Hello everyone, and thank you for attending this talk entitled Nature-Based Solutions for Coastal Defense, Key Aspects in the Modeling of Flow Ecosystem Interactions. Before we start, I would like to thank the local organizing committee for inviting me to give this talk and for making this virtual conference possible. I want to start with a brief motivation of the problem. We all know that coastal areas are very vulnerable and they are highly populated. In addition, the sea level rise or the change in the frequency and intensity of storms is increasing the risk to effects such as coastal flooding and erosion, leading to economic or even human losses. Because of that, new solutions have been requested. And looking for more sustainable measures, the solutions called nature-based solutions have emerged. As coastal engineers, we are all very familiar with this type of hard or gray solutions that have been studied for many decades. However, soft or green solutions based on natural ecosystems such as coral reefs, mangroves, salt marshes, or seagrasses are newer, and a deeper understanding of flow interaction with them is still needed. However, this is not an easy task, since we are dealing with different flow conditions, interacting with flexible or rigid elements that can be submerged or emerged. For that reason, two main approaches have been followed to study this interaction: numerical and experimental modeling. Both approaches deal with different scales. Large and small domains can be studied by using numerical modeling depending on the selected model. And when performing an experimental campaign, depending on the facility that is available and the type of study we want to perform, we will be able to run experiments at real scale, or we will need to use scaled models. Both approaches can be complementary, and they can be used to try to get the coastal protection service that an ecosystem is providing. Small-scale models and lab experiments allow us to better understand the detailed physics that are involved in the flow ecosystem interaction. Laboratory data is also used to validate those small-scale numerical models. And both give us new formulations and parameterizations that can be used to fit larger scale models, able to deal with an entire ecosystem and even more than one, using those parameterizations needed because those large scale models are simplifying the physics involved in the problem. So those new formulations and parameterizations from the small scale can help us in these larger scale models. So with this general picture of both approaches, I'm going to start with a brief description of some important aspects that should be considered in physical modeling. We can use physical modeling to study different processes at different scales, from tests run with one individual in turbulent processes, to cases where a whole community is considered, and then we have to leave the lab and move into the field. So the first step when planning an experimental campaign is to check the availability of the possible facilities, their characteristics, and then define the hydrodynamics and the ecosystem properties. And sometimes we will need to scale those hydrodynamic and ecosystem properties to fit in our facility. Another important aspect is to make the decision of running the experiments using real individuals or mimics. Regarding the different scales, the most important question to answer is which process we want to study. Then, if processes such as turbulent features or detailed velocity fields and forces want to be measured, we will choose techniques such as particle image velocimetry, PIV, and we will run the test at a small scale. If wave attenuation is the target of our experiments, we will need to build a sufficiently long ecosystem according to the tested wavelengths in order to be able to capture properly this wave attenuation. and simple devices such as free surface gauges will be enough to quantify this wave height decay. Finally, if we want to move to a larger scale, field measurements will be necessary. Then we will be using those devices that usually are used in the field, such as ADCPs or pressure sensors. Regarding the decision of using real individuals or mimics, here there are some pros and cons of both choices. Starting with the mimics, they are usually cheaper than real individuals. The process to build them can be optimized and plenty of them can be obtained. And they allow testing species that are protected or that cannot be grown because of its growing time. However, the main disadvantage is that they should properly represent the real individual's geometry and biomechanical properties, and that is not an easy task in many cases. Regarding the geometrical scaling, typical scaling follows in the lab, using Freud or Reynolds number similarities usually are used, depending on the processes that we want to study. When dealing with flexible individuals, parameters such as the hydraulic similarity parameter are used to reproduce the individual's behavior under the flow action. This parameter includes variables such as the density of the material used to build the mimics with respect to the flow density and its modulus of elasticity. This is an example of a Posidonia oceanica mimic, or several, subjected to oscillatory flow. As an example of experiments performed considering mimics, here is the representation of a mature Rhizophora forest at 1/6 scale, considering Freud similarity to scale the hydrodynamic conditions, and also Reynolds number similarity was considered by ensuring a sufficiently high Reynolds number in the model to ensure similarity in the wake structure between the model and the real conditions. A forest 26 meters long was built to analyze wave damping, and forces were measured in 9 mimics. Wave damping coefficient, beta in the equations, was used to get the wave decay. So the equation on the figure was used to fit the experimental data to get this wave decay. This wave decay was analyzed twice, first with the empty flume, and then with the flume full of mimics. Here you can see an example for one of the tested conditions, the hydrodynamic conditions, and the 3 different water depths, the 3 colors, for the flume, the empty flume, the dashed lines, and the flume full of mangroves, the solid lines. That means that 2 beta coefficients were obtained for each test. A beta for the flume full of mangroves and another one for the empty flume. This allows us to estimate the damping coefficient strictly due to the forest trees. That was called beta M. In the slide you can see the equation used to get that beta M. One question that we wanted to answer was, can we estimate the drag force, the most commonly used force in numerical models, from wave decay? Following analytical formulations, as shown in the screen, this drag force was computed for both cases, considering the beta coefficient directly obtained from the flume full of mangroves and the one after subtracting the walls and bottom friction of our facility. The results show that the drag force analytically obtained by considering the beta coefficient that consider only the action of the elements, that is removing our facility friction, meets very well the drag forces directly measured on the mimics. So, one of the key aspects derived from this study was that we need to check the additional friction that our facility is inducing in the flow when quantifying the energy attenuation provided by an ecosystem. Since, if not, we can be overestimating this attenuation. Second, wave damping coefficient obtained after subtracting the bottom and walls friction allow us to easily get an estimation of the drag force with a maximum relative error of 12% between that analytical solution and the forces measured in the lab. This facilitates the estimation of this force since wave decay is much easier to be quantified than drag forces. And finally, the submerged solid volume fraction of the forest, defined by using that equation for different water levels, allow us to get a common relationship between the damping coefficient and the relative wave height. That means that we were able to include the properties of the forest for the different water levels by means of this submerged solid volume fraction, highlighting the importance of this parameter. Another option to run our experiments is to use real mimics. The use of real individuals is essential to gain insight into their performance under the flow action. Also, that implies running the experiments at real scale, so we are avoiding any scaling issues. And they overcome the already exposed limitations inherent to the use of mimics. However, obtaining these real individuals is not easy, and also aspects such as individual survival and the need to ensure that their properties will be maintained through the experiments should be considered. So here is an example of experiments run with two species of salt marshes, Spartina and Puccinellia, that were subjected to waves and currents. Both species were grown from seeds. The main aspects obtained from these tests were, first, that both wave attenuation and flow divergence largely depend on the vegetation properties and the submergence ratio. The submergence ratio is defined as the ratio between the vegetation height and the water depth. The second main conclusion or aspect that we learned from these experiments was that wave damping coefficient was found to linearly relate to the meadow standing biomass. The meadow standing biomass is defined as the dry weight per unit area. This was found considering 5 values of biomass resulting from 2 densities for Spartina and 3 for Puccinellia. So, to extend that study with those 2 real vegetations, another study was performed, in this case taking the plants from the field. So, this study, the main objective was to answer the question that I was mentioning before, like the beta coefficient is actually linearly related to the standing biomass. Can the standing biomass be a key parameter determining the wave attenuation provided by different species of salt marshes? Well, if you want to know if this was found for those different species in this second round of tests, you can attend the session 113. So moving to the numerical modeling, again, different scales can be considered. And each one of them involves different studies in terms of the processes that can be studied, moving from the small scales dealing with individuals and viscous flow to large scales studying different ecosystems through energy balance models. Focusing on time domain models, we can differentiate two main groups: models dealing with potential flow and models resolving Navier-Stokes equations. The first ones usually introduce the effect of the ecosystems by an additional friction factor. The second ones, especially the ones dealing with Reynolds average Navier-Stokes equations, RANS equations, usually introduce a drag force into the momentum equation as a sink of momentum. Lagrangian approaches usually model the ecosystem individuals, avoiding parameterizations but implying high computational costs. Of course, the computational domains that can be resolved by the two groups are different, moving from few kilometers for potential flow models to meters for Navier-Stokes models. More simplified models, such as models dealing with spectral energy conservation equations, usually use friction or drag coefficients to define the amount of energy dissipated by the ecosystem in the energy balance. At global scales, 1D models use simplified analytical formulas to infer this energy decay. As it happens for physical modeling, each scale implies the possibility of studying different processes and then getting different results. Also, moving from the small scale to the large scale allow us to parameterize the physics that are not solved at the larger scales to finally be able to estimate the coastal protection service provided by a real ecosystem of hundreds of kilometers. As an example of numerical modeling, I'm going to present here a RANS model, IH-FOM, where a drag and an inertial force were implemented in the momentum equation to induce the energy damping produced by the ecosystem. The turbulent closure model was also modified to include the vegetation effects. IH-FOM also allows introducing the individual elements as obstacles, using in that case a k-omega SST turbulence closure model. The model was validated for both approaches with laboratory data. Here is an example of two simulations performed, including the individual elements. And also in the figure, you can see the well assessment of the wave decay obtained with the model, including the drag force. In both cases, the wave decay was well represented, but the computational time for the approach, including all the individual elements, was more than 3 times the time needed to run the drag approach. However, the drag approach relies on the proper definition of the drag coefficient, whereas the direct simulation of the individuals does not account for any parameterization and allow us to get the forces on the individuals or, for example, the detailed flow characteristics inside the field. So depending the question you want to answer, you can go for one or another. So after this example, this brings me to one of the first slides I showed you before. Just to emphasize that the different scales in both approaches should be linked to move forward in the accurate quantification of the coastal protection service that nature-based solutions can provide. And also, we have to think that both approaches can be connected and should be connected to enhance the strengths of both approaches and to move forward faster. So, after telling you all these different studies and showing you those examples, is that true? Is that possible? Can we follow that path? Can we move from the small scale to the large scale? Well, this is an example of a study where I think that yes, we can follow that path. And here I am just showing you a formula that was shown before, where the damping coefficient is obtained as a function of the submerged solid volume fraction of the forest. That fraction can be parameterized for different mangrove forests, considering their age. That way, we can get an estimation of the wave attenuation that a 30 years old mangrove forest can give us, just by plotting attenuation curves as the one shown in the slide. I want to point it out also that this highlights also the great importance of multidisciplinary teams in this type of nature-based solutions to move forward. To conclude, I just want to acknowledge all the funding sources that made possible the different studies presented here, and of course, all the co-authors of the different pieces of work partially presented in this presentation. Thank you very much for your attention.